At the end of the lesson, you are expected to identify the nature of maximum likelihood estimation, follow the process of obtaining the parameters, and appreciate the use of maximum likelihood in machine learning. In machine learning, our main goal is to always make or build the best model. And when we say the best model, it has something to do with the one that is the most sensible. And being sensible as far as machine learning model is concerned has something to do with selecting the best parameters. And these parameters must be able to make the most likely or just the more likely observations. And so in our study before, if you still remember this one, so in our mathematical and analytical process, we use the natural logarithm. So later we will discuss about why do we use the natural logarithm in maximum likelihood. So here we have estimated the arguments for w hat and the sigma squared, because these two, when properly estimated, would maximize the log likelihood and also the likelihood itself. And so because we consider our observation to be that of Gaussian, then we have substituted the expression for the Gaussian density function, and here we could see the separate parts of the function. And also here in this case, what we did here was that we substituted for the deterministic component, because this one gives us the log likelihood expression that tell us clearly the drift or the trend of our model. So before we continue, please hit the subscribe button to enjoy our deep learning, mastering machine learning algorithm, and natural language processing courses. You can always learn our data science tips. So why is it that we have to use the natural log? So first and foremost, the nature of our natural log is that it is monotonically increasing function. The word here is monotonic or monotone. Then it must be increasing. So what is the meaning of this one? So as you could see in here, we have three graphs. Number one is from this point going to this point, then it's increasing. Number two is from this point and going to this point, although there is a curve here, but then it's still increasing. And as you could see here in our number 3 graph, from this point it is increasing, but when it reaches the peak, it goes down and it goes up again. So as far as being monotonic is concerned, which of these 3 graphs are monotonic? So we said that it must be also increasing. So 1 and number 2, there is only one direction, so it is monotonic. It's going up and it's going up, and both of them are increasing. Okay, so here in graph number 3, you could see that the direction is twice. So it's going up and then it's going down. So it's up and down. So obviously we could see here that it is not monotonic. In fact, there are 2 directions, and even if there is an increasing trend here, but then we can also find that there is a decreasing one in this case. So clearly this is not monotonic. So what's the importance of having the natural log in our function, or using this in our function? So when you use the natural log, we could ensure that the starting point of the log of the probability and that of the original probability function is at exactly at the same point, or in some cases it would be at almost exactly the same point. So with this, when they start from or at the same point, or exactly at the same point, or almost exactly at the same point, then our work as data scientists would be also simpler. So how do we get the parameters of our model, especially that we are not just concerned with only one point? So we've been talking about the use of dataset for building our machine learning models, because we don't just deal with only one point, but we in most cases deal with a lot of attributes, even thousands of data points. So this is why we have to properly deal with the different parameters. So we said that we have the mu parameter, and also we have the sigma squared parameter, or that's what we call the variance. So how do we do it? How do we come up with the parameter w. So it's basic in our study that when we would like to optimize the parameter, what we do here is that we take the derivative and then we equate that into 0. And that is what we do in this case in finding the parameter w. So basically what we do here is that we take the derivative of w. The most important thing that we have to take note of in this case is that the partial derivative with respect to w is actually a vector. And so because it's a vector, we equate that into 0. So if you could recall, before we talked about how we could make or use a shorthand or matrix vector for our model building, and just for a very simple review. So we have here x, and then we have here t. So these are the attributes. And so we said that we first have to get the transpose version of each point of x. So we have here xt1, xt2, that's for point number 2, and so on and so forth. And of course, until we reach the last point. And then when we do that, we then augment it by adding 1. So from xt1, it becomes 1x1, because if we do like this, then it will be easier for us to process the data based on what the methodical and analytical processing of the data set. So if you could still remember, this one can be expressed as this. It's actually a summation. So starting from n1, having endpoints xn, then we have times tn. So this one gives the mathematical process of doing x and t. So again, this is a summation of the product of this and then this. So I had a lesson on that, please review, because having the proper understanding of how this process really goes analytically, then it will be easier for you to understand how the maximum likelihood as far as this kind of presentation is concerned really works. So when we present our case this way, then it would be very easy for us to write our derivative in vector or even in matrix form. So that is why the derivative matrix form of our data is now like this. So as you could see, this is actually just like this one, of course, because it's a vector or a matrix. And then we equate that into 0. And how do we optimize the value of w? So of course, again, we equate that into 0. And what we do here is that we do this process. So we divide that with the variance of the data. And we don't need to go through the step-by-step process of arriving from this point going to this point. So I would like to leave this one to you to process all of the different steps. And if you have some questions, you may just write down below the comments so we could discuss properly. And then when you do like this, the end result would be like this. Now, so this is the maximum likelihood solution for w. And so when you solve using, of course, different natural numbers, then the result of this would be the maximum likelihood of the parameter w. So as you could see, this kind of solution is the same or exactly the least square solutions. The thing that you have to remember is that when we minimize the squared loss, this is the same in saying that it is the same with the maximum likelihood solution, but we have to always remember that this presumes that the noise is that of a Gaussian. And maybe you would like to ask me, so where is then here the variance or the noise variance? Why is it that we cannot find here in this process? What's the effect? Although you could see in this part here that we divide this one with the noise variance, it actually affects somehow by scaling up the likelihood, but actually it does not affect the value of w. So assuming that we have already computed for the value of w hat, then the next thing that we're going to do is that we're going to obtain the expression for, or the value of, the sigma squared. And how do we do that? So just like what we did here before, so in sigma squared, we also equate this to 0. And as you could see, the same with our w hat, we also get the derivative or partial derivative with respect to sigma. And when we rearrange this expression, then we can get this one. So again, we don't have to go through the step-by-step of processing this expression from this point going to this point. I will leave that to you. So here, as you could see, we could see here that the variance is just the average squared loss. So for proper understanding, we're going again to use the matrix version of processing the value or the optimal value of our sigma squared. So we use this process to get the value, and when we substitute the value of w hat, this one, okay, so we could arrive at this expression. So what does sigma squared hat mean? So this tells us the variance of the Gaussian noise. Let me write here, this is the variance of the Gaussian noise. What is this for? Why do we have to study this? By being able to identify the different values of the parameters, we can be able to compare the different sets of models that can give us the best presentation of the picture of the observed data. After all being said and done, let's try this. What is the nature of maximum likelihood? How are the values of parameters obtained? Do we need to find only one value for each parameter? Why? Leave your answers in the comment below so that we would be able to have a very rich interaction of ideas and we can learn from each other. Do you want to know more about this course? Just click the card on your right screen. You can enjoy our deep learning, mastering machine learning algorithm, natural language processing, and data science tips. Learn and upskill for free.